This is part 12 of ELEC5300, lecture 11. Now we're going to look at how do we deal with the case where the noise does not satisfy the assumption that we had last time, where the noise was this kind of white noise process where each component was was correlated and the individual variances were all the same. Right? In general, the noise could be correlated, right, or at least non-equal variance, right? How do we deal with this? Well, we know that we can solve the case when the noise is white, right? And so we can do exactly the same thing we did with the Wiener filter and somehow implicitly with the Kalman filter. We just make the non-white measurements white by applying a linear transformation to them. Right? Now, we know that as long as this noise here is has a covariance matrix which is positive definite, right, so that there's kind of noise components in all directions, right, then we can always find a linear transformation that makes the measurement noise uncorrelated. Right, so we can find a gamma such that W is equal to gamma times V, where this new set of noises are white. Right? Now, of course, when we do that, we're also going to transform the x's, so we're going to have to do a little bit of work to do that. But we know that we can always do this. And so now, since we generally assume that the measurement noises are zero mean, we don't really have to worry about whether we're dealing with the covariance matrix or the autocorrelation matrix. Now, remember that the autocorrelation or the covariance matrix, they're always symmetric and positive semi-definite. We're going to assume here that actually it's positive definite so that there's no zero eigenvalue. So there must exist an orthogonal matrix then in that case where I can diagonalize the correlation matrix or equivalently the covariance matrix. And so this is a diagonal matrix of eigenvalues here, which I'm going to assume are all positive. Now, this is an orthogonal matrix, right? So therefore, the inverse is equal to the transpose, so I can also write this. This is equivalent just by replacing this by this inside here. I can also write this using the eigenvalue equation as we saw earlier. So the desired linear transformation of the data is just to multiply by some matrix here that depends on that eigenvalue decomposition. In particular, what I'm going to do is I'm going to multiply by phi transpose, and then divide by each measurement by 1 over lambda I, so 1 over square root of lambda. Right? So that's given by this diagonal matrix here. And if I transpose that, then I'm going to flip the order, but this is diagonal, so it doesn't make any difference, and the transpose of this is that. So then I can easily prove that this is going to be white. This is kind of the exact same thing we did earlier. So I just say, well, expected the correlation matrix of W is just gamma times the correlation matrix of V times gamma transpose. I substitute in gamma, I get this. This diagonalizes R inside here, and then I get lambda, and then this thing reduces to 1. And you can also show that since gamma R gamma transpose is equal to 1, right, then I can left multiply by gamma inverse. I can right multiply by gamma transpose inverse, right, but gamma transpose inverse is just gamma, and so I just get R inverse is just equal to gamma transpose times gamma, just by inverting these two and switching the order. Now we consider the transform measurement. Z is equal to gamma times y. Right? And so now when I do that, y is equal to hx plus v. You can see here I apply gamma to the noise, right? But I've also changed the measurements, right? So z, the relationship between z and x is not the same as the relationship between y and x, right? So I have this new function here, but this is just another readout matrix, right? All I've done is kind of change the readout matrix y a little bit by adding this gamma inside here, right? Now, since the noise here is white, though, I can apply our previous result. Just instead of using H, I just use G, right? So this is the application of the previous result, and then I simply stick in the form for G, which is gamma H, inside here. Then you can see here from our previous result on the previous page, this thing here shows up, and this thing here shows up. And from the previous page, right down here, that's R inverse. And so this result here is the Gauss-Markov theorem. You can see here what we've done is we've done exactly the same trick that we did with the Wiener filter, the Kalman filter. We dealt with a situation which was not white by just transforming it to the white noise case and solving it there, and then doing a substitution just to express everything in terms of the original non-whitened data Y.